Hi everyone, I am Vivek Gupta presenting XInfoTabS, evaluating multilingual tabular natural language inference. So let's first introduce what is tabular inference. So tabular inference is similar to standard natural language inference, except that the premise here is a table, and the task is given the table premise and a hypothesis statement. You have to predict whether it's true, entail, false, contradict, or undetermined neutral. So here you can see in the example in the right, there is a table about boxing, and then there is a hypothesis statement. The modern form of boxing starting in late 1900s. You can see the boxing started in 1904, which is early 1900. So this is a contradiction. You can see more details in the InfoTabS paper about this task. A main motivation behind this paper is there's no work which is done in the multilingual tabular inference space. All the existing work right now exists only in English. Through this work, we want to address these two questions. First is, how can we create a dataset that can be leveraged to train and evaluate multimodal models for this hard, challenging tabular inference task? How well does this multilingual model reason about multilingual tabular inference? And in this case, we considered like models like which are multilingual, XLM, Robota, and Number in a study. A claim is, for tabular natural language inference, it's not enough to only focus in English. Progress in tabular inference must be made across the board, and this include all languages. A main contribution is, we introduce XInfoTabS. It's a multilingual dataset for semi-structured tabular inference. It contains languages, 10 diverse languages from across various regions in the world. To create XInfoTabS, we leverage state-of-art machine translation models. We provide, which can do high quality translation, and we adapt a very simple but effective pipeline for translating tables. We also did high automatic and thorough human evaluation to check the quality of XInfoTabS. We also check how this multilingual models, when we are trained and evaluated on across various training strategies, perform over this challenging task of multilingual tabular inference on XInfoTabS. So this is an example of XInfoTabS. As you can see, the same table in English boxing is now translated to French, and then there is hypothesis, different hypotheses from various languages in this. So the task is given this table in different language and the hypothesis in different language. We have to see if this model can reason on this. So first step in the translation is, we basically take the table and linearize the row. So we take each row separately as a translation and consider them as a joint unit. The key value basically has a joint unit for translation. First, we found that the models actually do a lot of translate for even name entities and numbers, so which is not correct. They should be transliterated. So to avoid this doing, we basically highlighted the model with quotes, the name entities in the quotes, so that the model doesn't translate them instead transliterate them. Next, we basically add more additional context for better translation. We found that adding context like the category information is beneficial. Otherwise, the key can be inferred in a wrong way. For example, the focus is very different in sports as well as in study terms, or the parenthood is any different meaning in different context versus sport context. So adding context like it's a sport table, sport is beneficial. Also, we use the delimiter vertical bar to separate, because this really help in extracting in the later stages of pipeline. Next, we basically did the translation for each row separately, one after another. We use different models for different translation, which we found was beneficial, and for that we discuss in the next section how we choose a model for translation for different language and different table or structure type. Next step is basically we start decontextualizing it. So we remove the category information. Since we use the delimiter it's easy to separate. We replace it by colon. We first remove the sports information, the category information, then we replace with the colon and semicolon. We remove the highlighting of the name entities, so it's NER de-highlighting, and finally we convert that to the original tabular format which we have. So now your table is basically converted to again a table. To measure the quality of translations, we employ multiple metrics. One is human and the rest three are automatic. So we first use paraphrase scores, which we basically capture the similarity between the original table sentence or hypothesis sentence and then the back translated version of the translated text, or the XInfoTabS data. So the XInfoTabS data is again converted to the English sentence with the same model. And here we use sentence BERT model like MPNet version 2, which is very powerful in capturing similarity, and we use the similarity, cosine similarity, to capture how much it's similar. Now, since this is using back translation, it do bring errors in the second phase when we translate from the translated language, let's say French, to again back to English. To avoid this, we also use a multilingual paraphrase source, which directly compare embeddings in the original and the translated text. So it's English versus the French translation, let's say, we're doing. We also use BERT score. This is again on the back translated thing only, but this and BERT score as well as MBERT score kind of thing to evaluate how model do, and this is shown to be very effective. And lastly, we did a lot of human evaluation, where we basically employ 5 annotators which do 500 examples per model per language, and we follow the annotation guideline from Cohen and Mons 2016 WMT task. We formed the same guidelines and then basically use the intent agreement to see the quality of our translation. So all details in the paper. So we overall, like individual details are there in the paper, but overall we found that for high resource thing, like we found that for high resource thing, like bilingual models are pretty much doing better. But for the low resource setting, we found that multilingual models like Marian MT and M2M are doing pretty good, which is expected as shown in the earlier task. Like translations is better with a multilingual model, especially for low resource setting. So we also found that we use bilingual for the high resource and multilingual for this. There are also differences in the structure, like hypothesis versus this. We found some cases where different models used for hypothesis and the table. More details are there in the paper. Similar to InfoTabS, we also have 3 splits, and we found that this is important for mitigating artifacts. So first split is alpha 1, which is very similar to the train set. It contains tables from the same domain. The second is the adversarial split alpha 2, which has although table from the same domain, but the hypothesis up perturbed by 1 or 2 tokens, like before to after, over to under, so is that the label is flipped. So intel become contradict become intel, and vice versa. So this is alpha 2, and then the alpha 3 is the 0 shot setting, where we have tables from very different domain, cross domain, and you can see the key overlap between the train and the set is very minimal. So these has keys which are very different in this setting. Next, we evaluate how this multilingual model do perform on this task of multilingual tabular inference. And first we try is translated test baseline, which is basically we train the model on InfoTabS data set, which is English premise, English sentence. For the test thing, we first back translated them to English. So basically have our data which is in multiple languages, we translate back to English using a model, the same model in which they are translated, and then we basically train. So we found that here XLM Robota performed well, and the accuracy highest was with XLM Robota, which is 70. We found that if we do a language specific training, since we have XInfoTabS which is on multiple language, can we help? So instead of back translated to English, we basically do language specific training. This is like multiple bilingual models which are trained on like English train on English, French is trained on French and French data. Both the training and the testing is done on the same languages. So this obviously performed better, although we found improvement in the MBERT, but we found substantial improvement of 2 to 3% in the XLM Robota setting. We further improve once we also do multiple language fine tuning. So first we check in this English only fine tuning. So the idea is basically we do 2 fine tunings. One is pre fine tuning on English, followed by language specific fine tuning. So this just has the difference from the last is there again multiple bilingual models, but each model is basically first trained on English to better equip with the task, and then train on our language specific to do this task. And we found that this further improved by 1%, and more importantly it improved the MBERT model, very similar to the original performance which were there in the English translate setting. Lastly, what we did is we take all the languages which we have and train them sequentially, starting from English, then high resource languages to low resource. We found this sequential nature is really beneficial, and then we use this for training, and we found this further improved by 1 or 2% of our performance, although it slightly improved the MBERT performance, but it still was better than language specific tuning. And this main advantage give a single unified multilingual model which we can basically test on all languages now. So it has reduced basically the model multiple models, space and time constraint. It just has one single model which is trained on all the languages which we have in the XInfoTabS. Lastly, we also tried a new task which is similar to the multilingual task, which is bilingual inference, where we have English premise and multilingual hypothesis. And in this we want to basically do, this is very real in the real world, is like the facts are mostly in the language. The fact here is the tables which are in English languages, mostly in English, but the claims are made in multiple languages. This is very common in the fact verification world and all. We also checked this and we found that this task is really challenging. Although the performance drastically dropped, but it was still better than the language specific training. It was equally but around language specific training, but Ember started performing really bad. So this is something which can be explored future in a separate work or something. We do all this on alpha 1, and this is the average score. For individual model score and all, I encourage you to visit the paper. Obviously, we found that XLM Robota perform better. High resource do much better than the low resource. XLM Robota better because there is more parameter, better learning objective, longer training time, and more languages in it. We also did a cross language model consistency analysis. So what you are seeing in the figure is like the each number basically can represent comparison of English with a high, medium, and low resource language. For high we use French, for medium we use African, and low we use Hindi. And we basically compare model consistency and inconsistency. Inconsistency is basically, so English, if for example it's predict entail, what does the model predict when it basically translated to another language, let's say French. So that's basically want to check, and if the models change its prediction, then we count this as a flip, which is inconsistent prediction. So the model is doing inconsistently predicting on different languages, and here we use a single model to basically check all these languages. So and consistency is when basically it's retain its labels even when translated on different languages, language invariant in short. We found that there is significant amount of inconsistency. Specifically, entail is getting a lot of flip to contradiction, much higher than the entail to neutral. Contradict to neutral is also very significant, specifically for the low resource settings and medium resource. Neutral to entail and neutral to contradict were equally flipped. We also did language specific analysis, and we found that entail to contradict was higher for like low resource and high resource, but was okay for the medium. Contradict to entail was much higher for the low resource, and it decreased for high resource. Entail to neutral was high for the low and the medium, but okay for the mid resource, and neutral to entail was very high for the low resource language, which was expected. Lastly, we also look at the consistency matrix. So we found that for low resource, the model wrongly predict entail for contradiction. It should have predict entailment, but it predict contradictions. In addition, for Hindi, the model predict neutral for entailment instances. This can be seen for a future work why this is happening and how can we improve the model around it. Thank you.